I wanted to go out and find a challenging physics problem for everyone, and then if give you a chance to solve it, and then if you have any problems, here's the video to help you solve it. So it says a basketball player who is standing 15 feet away from a basketball hoop is trying to make a basket. If the height of the hoop is 10 feet and the height at which the player shoots the ball is 6 feet, at what angle and with what speed should the player shoot the ball? Okay, so the question states something implicit that isn't quite shown in this picture, and so I want to point that out. It says that the player shoots the ball from 6 feet high. So from here to here is 6 feet. And that means that our ground level is really here. Or we could move that down to right there. So that's our ground level. So really we're asking, what is the distance from here to here? So that's 4 feet. So delta y is equal to 4 feet. So the question is really asking, at what velocity and angle do you have to shoot a ball in order to get it to go up 4 feet and over 15 feet? And so the first thing we want to do is define all of our known variables and figure out what is unknown. So there's a kinematics equation, so we need to know our changes of location, or our delta y, for example, is 4 feet, but we're using SI units, so let's go ahead and convert that. That is 1.2192 meters. If you don't know how to convert that, kindly go back to your pre-algebra class and relearn how to do that before continuing. And then part 2, we know delta x is equal to 15 feet, which is approximately 4.572 meters. And then the last thing we know, the last explicitly known variable is the acceleration. It's due to gravity alone, so it's negative 9.8 meters per second squared. And we're discounting the friction due to air. So essentially, air is not taking part in our physics problem. So what do we not know? We don't know what the initial velocity is. We don't know precisely for sure what the final velocity is, though we can discuss that here in a second. And then we don't know how much time it took. And so those are all key important variables in a kinematics equation, and we have to figure out how to get around knowing those. Now, as far as the final velocity goes, if we just said that final position is in the hoop, then we could set it up to where final velocity equals 0, where he shot it straight in the hoop. But that means every other possible way of shooting in the hoop, which is going all the way up and coming back down, or just having a shallow hoop, none of those would matter, because if it went straight to the hoop, it couldn't have any arch on it at all. And so if we just set final velocity equal to 0, that would preclude a number of other possible answers. And so the first thing that points out is there are more than one answer to this problem. There's the answer of going straight in, there's the answer of it going up and back in. And so we want to explore what's a good clean way of finding every possible solution with one equation. And so the first thing we're going to do to solve this is we're going to set up an equation that will allow us to know exactly how much time it took to go up and then back down. So if we look at a graph of time versus delta y, that looks more like an x, but that's delta y. So time versus delta y, we know that as the ball will start to go up, and then whenever it gets to its highest point, it will start to go back down. And at this point right here, this delta y is the hoop, and so at this point and at this point, the ball has reached the height of the hoop, but we want to know this one right here. So we want to know not only what time it got to the height of the hoop, but what time it got to the height of the hoop as it's coming back down. So we start with our equation delta y is equal to the initial velocity in the y direction times time plus 1/2 of the acceleration times time squared. And then we can rearrange this so that we have it in the form of, we want it in the form of ax squared plus bx plus c equals 0. So first of all, we got to make it equal 0, so we put delta y minus v initial in the y direction times t plus minus 1/2 at squared equals 0. And then we can rearrange that to get it in the form of ax squared plus bx plus c, which would make it negative 1/2 a t squared minus v initial y t plus delta y equals 0. And sometimes, just to simplify, what we can do is we can look at this negative 1/2 of a. A is a negative number itself. It's negative 9.8, so it's kind of simpler if we just make this a positive 4.9 t squared minus v initial y times t plus delta y equals 0. And then if you wanted to, you could even replace delta y with 1.2192, but it's not necessary. It's not necessary to replace anything. It just it makes it easier on the eyes if there's not a negative in the front. And so we're going to solve for t by using the quadratic formula. So t is equal to so the quadratic formula says that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And so we got to take all the corresponding points. So negative b, our b value is negative v initial y. So negative of negative v initial y is positive v initial y plus or minus the square root of negative v initial y squared. So when you square a negative, you get a positive number. So we can just do away with that and just put v initial y squared minus 4ac. So minus 4 times, we could put negative 1/2 a, or I just put 4.9. So minus 4.9 ac, so times 1.2192. And I'm putting the numbers in here right away so that we can analyze this very quickly. And all of that multiplied by 2a. So 2a is 1/2 of a, so or negative 1/2 of a being a negative number itself. It would be basically 4.9. So 2 times 1/2 makes it 1. So you get 9.8 down here, a positive number, as the denominator. And so this shows that we have two possible answers for t. And so we have basically two answers for time, and we're going to call that t1 and t2. So t1 is if we were to subtract, and t2 would be if we were to add. And so first of all, the first thing to note is that if v initial y squared, if the squared of the initial velocity in the y direction is equal to 4 times 4.9 times 1.2192, if that is equal to that, then you get 0 under the square root, under the root. So you would have the same answer on the top and the bottom if v initial y squared was equal to this. So if this all equaled 0, t1 would equal t2. And basically what that corresponds to is, like we said, if we shot here's the basketball and here's the hoop. If we shot it straight into the hoop and it didn't have any arch on it, that's what that would correspond to if v initial y squared was equal to the rest of that number. And so the second thing we need to notice is that when we shoot this ball up, it comes to the height of the hoop right here and right here. And so t1 is whenever you subtract, t1 is always going to be a smaller number than t2. And so that corresponds to as the ball is rising, and t2 corresponds to as the ball is falling through the net. So if v initial y squared were to equal the rest of this, that would correspond to a parabola that touches the point where you're looking for, and if it's anything greater than that, that corresponds to a parabola that has two intersections, or we would call it two real roots. And so because t2 is what corresponds to falling through the basketball hoop, we're going to use the equation for t2 throughout the rest of the solution. So just really quickly, let's analyze some things really quick. So we have here 4 times 4.9 times 1.2192, and that equals 23.896 roughly. So we're saying if v initial y squared equaled that number, so v initial y squared equaled that, we would have basically 23.8 minus 23.8. And that gives us our first clue to the answer as well, because we know that v initial y squared has to be greater than or equal to, so v initial y squared has to be greater than or equal to 4 times negative 1/2 a times delta y. And so it has to be greater than or equal to 23.896 in order to get a real answer. And that's the second part of the clue. We can pick any initial velocity in the y direction, and we can use that to solve what velocity we would need in the x direction, as long as that velocity is greater than the square root of 23.89, which is 4.888386 meters per second. So as long as the initial velocity moving straight upward is greater than or equal to 4.888386, you can pick what number it is and then solve for the velocity in the x direction using that number. So part 2, we need to find the initial velocity in the x direction. So the initial velocity in the x direction has no acceleration, so the formula is very simple. It's equal to delta x over t. Now, and that's a poor t, so let's try to draw it better. Now, all we have to do is replace t with our formula for t2, our equation for t2. So we get v initial x is equal to delta x divided by, it's going to be long, v initial y plus the square root of v initial y squared minus 4 times 4.9 times 1.2192 divided by 9.8. And so we can actually rearrange that, and which would put the 9.8 on the top. So delta x times 9.8 over the rest of this. And so when you do that, delta x, we know what delta x is. It's 15 feet, or approximately 4.572 meters. So whenever you multiply that by 9.8, you get v initial x is equal to 44.8056 divided by v initial y plus the square root of v initial y squared minus 4 times 4.9 times 1.2192. Now we see that there's only one unknown variable on the right side of the equation. It's v initial y, which it's hard to distinguish the difference between my v initial x and my v initial y. I apologize for that. But v initial y, and we just said that we can pick v initial y as long as that value is greater than 4.888386. And so we're going to pick, and since, just to keep it easy, I'll stick with 4.888386 because that causes this whole value to turn to 0. 4.888386 squared equals 4 times 4.9 times 1.2142. So I'm going to pick that number, and that turns that whole value to 0, and I can simplify my equation even further. And so what I end up with is that v initial in the x direction is equal to 44.8056 divided by 4.888386, which is equal to 9.166 meters per second. So that's my v initial in the x direction right here. This is my v initial in the y direction right here. And so now I can use the Pythagorean theorem to solve for the v initial, the vector quantity of v initial. So v initial is equal to the square root of v initial x squared plus v initial y squared. So v initial is equal to the square root of 9.166 squared plus 4.888386 squared, which is equal to 10.39 meters per second. Now the last thing you need to know is the angle, and so every all out of the infinite number of initial velocities that you could possibly have, each of them is going to have a different angle because you're going to have a different upward speed and a different speed in the x direction. So you just have to use the sine function. So sine theta is equal, and there's my theta, is equal to opposite over hypotenuse. The hypotenuse would be v initial. The opposite would end up being the v initial in the y direction. And so you use the inverse sine. So theta is equal to sine, the inverse sine, times opposite over hypotenuse. Move all this stuff up out of the way. And you get that theta is equal to the inverse sine of 4.888386 over 10.39, which is equal to 28.06 degrees. 28.06 degrees.